Question number 13. Explain that the speed of sound varies with different mediums and temperature. Sound is a mechanical wave because it needs medium to travel, like it needs solid, liquid and gas. Speed of sound is fastest through solid because the particles are tightly packed. It is easy to vibrate. It is easy to disturb the neighboring particles, so the speed is the greatest through the solid, and through the liquid it is medium, and the slowest speed through the gas. And here is the inequality, the greatest for the solid and then following liquid gas. Approximately the solid speed of sound through the solid 5000, 6000, 7000, it depends on the density of the solid, and for the liquid it is 1500, 400, depends on the liquid type of liquid, density of the liquid. And for the gas 330, 340, 350, it depends on the temperature and the density of the gas. And next, speed of sound and temperature. Now we have air, medium, gas. If the air is at the high temperature, air particles are moving faster and collide more often. Sound travels faster. So if the temperature is higher, speed of sound is higher, greatest. If the temperature is lower, speed of sound also slower because of the particles, the movement of the particles. Temperature increases, movement of the particles increases. Now we have approximate rule. Speed of sound increases by 0.6 meter per second for every 1 degree Celsius if increase in temperature. Now we have an example. When the temperature of air is 20 degrees Celsius and the speed of sound is 343 meter per second. If the temperature of the gas is 25 degrees Celsius, which means 5 degrees Celsius is increased, what is the new speed of sound? So first we have to find the speed for the change. So what is the temperature change? 5 degree Celsius. So each degree Celsius, the increase in velocity is 0.6 meter per second. So if you multiply 5 times 0.6, you get 3 meter per second. This will be added to the speed of sound given for 20 degrees Celsius. So 343 plus 3, 346 meter per second. You can pause and copy the every pages. Next question. Define sound pitch and relate it to the frequency of sound wave. Define loudness and relate it to amplitude of a sound wave. Pitch is the highness and lowness of a sound as we perceive it. High pitch, high frequency. You can see more number of waves. Low pitch, low frequency, less number of waves per second. Frequency means number of waves per second. Now if you see the middle C, the frequency value 262. For the piano, the frequency is 4186. So the middle C has lower frequency, low pitch. The piano has high frequency, high pitch. So pitch is related to the frequency. And next, define loudness and relate it to the amplitude. Loudness, what is loudness? It is how strong or intense a sound seems to our ears. Large amplitude means louder. Small amplitude, softer. Large amplitude means the height of the wave is the higher amplitude, and this height of the wave is smaller, so soft. This is loud and this is soft. Amplitude equal to measure of pressure variation, and greater pressure variation is equal to more intense. If the pressure variation is big and the sound intensity is higher, greater loudness is equal to more decibel, because the loudness is measured by decibel dB. If the pressure, the higher the pressure, greater the decibel. Now you have some picture here. You can see the height of the wave here. You check, this one is bigger, so this is louder, this is softer. Amplitude is smaller for the softer. And here you can count the number of waves, 1, here 2. In the same length, here also 1 and 2. Number of waves are the same, so these two picture are having same pitch, because same number of waves, same pitch. Now we can check here. Here the height of the wave is bigger than the second one, so this one we can say louder, and this is soft. And here number of waves are less, so low pitch. More number of waves, high pitch. Low pitch is equal to low frequency, high pitch is equal to high frequency. Some more examples. You can check the amplitude is here shorter, so it is soft sound. The amplitude is longer, so it is louder. And the amplitude is here more, so it is loud. Amplitude, the height is small, so it is soft. Here less number of waves, low pitch. More number of waves, high pitch. Same here, soft, high pitch, because more number of waves. This is loud, low pitch, because less number of waves. You can see here more number of waves, high pitch, less number of waves, low pitch. The height of the wave is same, so the loudness is the same loud. Here the height is shorter, so it is soft sound, and this is tallest, so it is louder. And here you can count number of waves, 1, 2, 3. Here 1, 2, 3. Same number of waves, so same pitch. There is no pitch difference. No pitch difference. Now another important question. How much more intense is 80 decibel than a 40 decibel? Now first step, you should find the difference of the decibel, delta. Delta means change. 80 minus 40 is equal to 40 decibel. Now we are going to find how much more intense. So in order to find how much more intense, we have a formula, 10 to the power delta B over 10. So in the place of delta B, you can insert 40 divided by, because we found here 40, divided by 10. So 40 by 10 is 4. 10 to the power 4 is 10,000. So 80 decibel is 10,000 times more intense than 40 decibel. Next, we have defined the Doppler effect. Explain the Doppler effect of sound. You can pause the video and you can copy it down. Source moving towards the observer. Now here you can see there are two observers in this picture. Here is observer A, observer B, and here is a source. And the source is moving towards the observer A. So he perceives or receives higher frequency. And this lady observer B perceives or receives lower frequency. He will get high pitch. This lady will get low pitch. Because here the number of waves per second increases, because the waves are getting compressed. Here the waves are getting spread out. So here lower frequency, and towards the observer A more number of waves, higher frequency, high pitch. And then for observer B more space between the waves, so she perceives less number of waves in every second. So she will be getting lower frequency and low pitch, because the source is moving towards the observer A. Okay, so here this is what it's written: source moving towards observer A. If it is moving observer A, what happens? High pitch. Why there is a high pitch? Because high frequency. Why there is a high frequency? Because the wavelengths are becoming shorter. Wavelengths are becoming shorter. Why wavelengths are shorter? Because wave crest gets compressed as it is moving. The source is moving towards the observer A. And just it is opposite for observer B. Observer B, she is getting lower pitch. It's a lower frequency, because few waves in every second. Wavelength become bigger because the wave crest gets spread out. You can pause and you can copy it down. Now, observer moving towards or away from a stationary source. Now, observer is moving. For example, here is a source. Here is a sound source, and the observer is here, and he is moving towards the source or moving away from the source. If he is moving towards the source, frequency increases, getting higher pitch. If he is moving away from the source, he perceives or receives lower frequency, less number of waves he will get, and the frequency reduces, low pitch. And we have formula here: Fd is equal to Fs V plus or minus Vd, V plus or minus Vs. Fd, detector or the observer frequency. Fs, source frequency. V, speed of sound. Vd, speed of detector. Vs, speed of source. If detector is not moving, Vd 0. If the source not moving, source of the speed of source 0. If anyone is moving, if the detector is moving towards the speed of sound, towards the direction of sound, Vd is positive. This is the direction of speed. If the detector is moving away from the opposite direction of the speed of sound or the direction of sound, Vd will be negative. The same applicable for the Vs. The speed of sound, the direction of sound is to the right, and the source of Vs, the speed of source is opposite, and it is negative. And this is the direction of speed, and the speed of source also moving towards the speed of sound, and it will be positive.